All right. Let's get started so that we can move through this and get into lunch. Thank you so much for having me here. I am Mike Place. I am from Salt Lake City, Utah. So I am a little ways from home, but it's been really wonderful to come out here. I am on the core engineering team at SaltStack. SaltStack, as you may know, is a configuration management and server automation framework. It sits in the same space as our friends at Chef and Puppet and Ansible and what have you. Salt is a Python-based open source project. It's on GitHub. And yeah, so I maintain that project. If you're a Salt contributor, thank you very much. I do appreciate it. I'm the guy that reviews all the pull requests and what have you. So today I want to talk about event-driven infrastructure. And one of the things that we try to do in our office is make sure that everything is question-driven. We have a philosophy that it's much better to focus on asking the right question than trying to rush to a quick answer. And so as I prepared this presentation, one of the things that I've tried to do is leave many of the conclusions somewhat open-ended. And so it's my hope that at the end of this, even if we don't wrap things up into a nice bow, that at least hopefully you'll have some questions that you can take back to your teams to ask them and ask yourselves about the way you've designed your infrastructure and the way you do things day to day. So I want to start with a statement. Automation brought us new tool chains, and DevOps brought us new culture. Well, what now? And one of the things that I've come to realize as I go from place to place is that one of the important ways to look at computing and modern infrastructure and even modern culture is to ask where it is that we've been. Where has all of this come from? For example, when we spent most of 2016 talking about Docker and containers. And we have to ask ourselves first, in order to understand Docker and containers, where did all of this come from, right? And of course, the answer is that, that stuff is built on technology that is now many years old. Started with CH root jails and went into C groups and so on and so forth. And one of the things, or one of the technologies that I think modern infrastructure is built on are the principles of distributed computing. And so I want to start by talking a little bit about distributed computing before we lead into the idea of event-driven automation and what it can do for us. So I think there are three pillars of distributed computing. The first, the ability for the system to be aware of the existence and capability of its member nodes, right? We call this service discovery, right? The second, the ability to coordinate tasks between those nodes, right? We call this a scheduler. The last is inter-process communication, which can connect almost any node in the system to any other. Now, when I talk about distributed computing, sometimes people think I'm talking about parallel computing with shared memory architectures and all of that. I'm not. I'm talking simply about any sort of computing infrastructure which contains these three components. And I think that if you think about that modern infrastructure simply in these simple terms, you'll start to recognize these principles in the infrastructure that you've built today. For example, going back to containerization, one of the ways that I think about containerization is simply moving back to the idea of a distributed operating system and thinking about a container as a single process on that operating system. And if you do so, I think you have to ask yourself, okay, fine, I've got all these processes running on a distributed system. What's the inter-process communication mechanism going to look like? And that's what we're going to talk about today. IPC in a distributed operating system is effectively just called a message bus. And message buses, I think, are a critical component that we don't talk enough about. So what are the properties of a message bus? First, a message bus has a data model, right? We know how to exchange data between processes, between nodes on these operating systems because effectively they speak the same language. We have a command set for communicating that data, right? In regular IPC, this all comes from the C library. And we have a transport infrastructure to communicate that data between endpoints. So, trying to connect this back to DevOps, right, which is what we're here to discuss, I'm going to make the claim that we already have message buses built for operations. Okay, what are those message buses? Well, we have things like monitoring, right? We have central nodes which go out and try to connect to services, figure out what the state of those services are. We have services which report their state back to central aggregation points to do graphing and what have you. We have configuration management, which I think is a logical message bus for for operations. The notion that we have a command and control system that can perform remote execution tasks on remote nodes and report back the status of those tasks. We have things like chat ops. We can do things like auto-scaling across this message bus, right? We have, for example, Amazon's Lambda, which is a wonderful example of what a message bus can do in modern infrastructure. And of course, one of the primary responsibilities of a message bus for operations is provisioning, right? It's a common framework that has the properties discussed before that can provision new hosts, new containers, new services, what have you. So I think on the other side of that, we also have message buses for developers, or better put, for applications, right? Anything that connects various levels of an application stack, I think has a message bus of some kind, right? Sometimes these are simply streaming APIs between services. Sometimes they're set up and torn down on demand. But the question that the first question that I want us to consider about our own infrastructures and consider bringing back to our teams. In DevOps, we talk a lot about connecting these two sides. Well, what happens if we examine both of those types of message buses and we consider the possibilities that could emerge when those formerly siloed streams of events are shared with each other, right? What happens if we give our configuration management layer insight and understanding into the monitoring layer, for example? Those are the sorts of questions we're going to be discussing for the rest of this talk. So the first question is, what does most automation look like right now? I spend all my day building SaltStack, and I think about this question from time to time. Most automation right now is effectively packaged workflows. If you remember early on, back in the sort of the birth of DevOps, as it were, we were promised infrastructure as code, right? And that sounded really nice at the time. I thought, well, that's very attractive. And what we got effectively, and much of this is my fault if you want to lay some blame, is we got sort of series of steps that we would list out. We would go do these steps a little bit, and we had a little bit of abstraction. We had a little bit of error control. We had a lot of effectively imperative frameworks, right? We would say, okay, this is how we can describe an infrastructure, and we're going to use, and the debate is really going to be, oh, shall we use YAML or JSON, or shall we use a DSL to describe this infrastructure? And much of the time, this was focused around provisioning. These workflows were effectively initiated by lazy humans. And I think even today, it's fair to say that despite our best efforts, this stuff can be very brittle. And the reason that it's brittle, I think, at the end of the day is something that should be obvious if we think about it, which is that despite all our best efforts at monitoring and looking at graphs and trying to have stand-ups and what have you during the day, we're still not really great at understanding the state of our systems, especially the state of the system at the point that we engage automation, right? We still make a lot of assumptions even today. And for example, like in the Salt world, some of the questions are like, okay, well, how do I test and make sure my infrastructure is in a proper state before I run it? Well, you can go out and you can test against, your intended declaration, and that gives you a binary answer about, yes or no, am I in compliance? But that's not a particularly in-depth understanding of what's going on. And I think most importantly, this doesn't really feel much like programming, right? When DevOps launched, I was promised infrastructure as code. And what I got was, again, this declarative imperative debate. But what I wanted was, code, real code. I wanted to be able to do things like callbacks, right? And introduce some asynchronicity and actually be able to program my infrastructure beyond simply declaring what this provisioning state ought to look like. So the question that I want to focus on for the rest of this is, okay, how can we move beyond that? How can we extend that model? So the area that I look at in thinking about this is event-driven programming, right? Event-driven programming, for people who don't know, it's a paradigm where the flow of the program is determined by events, right? By user actions. Event-driven programming is probably made most famous by people that write GUIs, as much as I don't like GUIs. Effectively, you register for events, right? You wait for them to occur, and when they do occur, you perform some action, right? So what are the principles of event-driven programming, right? Node.js was very early to this party. Like I mentioned, most GUI applications on the desktop have some form of event-driven programming, and pretty much anything on iOS, right, is all event-driven. And as horrible as all of that stuff is, I think there is a lesson for us here, right? There are 3 principles in event-driven programming that I think are worth noting. First, you have a set of functions which can handle events, right? Depending on the implementation, these can be blocking, they can be non-blocking, what have you. You need a mechanism for binding registered functions to events, right? And last, you need a main loop, or loops if you're very brave, which can consistently poll for new events and call matching event handlers that can take action whenever an event is received. Now, I think it's important to be honest and talk about the criticisms of event-driven programming, of which there are many, all right? One is that writing procedures to perform steps in a particular order is not always easy. This is at the imperative side of things. On the other side, we have declarative, right? We're describing the intended state of a system without explicitly describing the steps to achieve that state. That's the declarative approach. Highly asynchronous code can be difficult to troubleshoot. I think that's true wherever you go. And it takes a mind shift to think about imperative and declarative approaches melded into one, which I think is what event-driven programming ultimately looks like, and that can create some confusion. And it can be challenging to translate procedural workflows into something asynchronous and event-driven. But I think at the same time, event-driven programming has a number of advantages. First, I think it's easy to find natural dividing lines for unit testing one's infrastructure. It's highly composable. And I think most importantly, event-driven programming, or as we'll see, event-driven infrastructure, makes it very easy and simple to have a common platform for both the dev side and the ops side to speak. Okay, so if you have a singular message bus, a singular plane for your application to put telemetry events onto, that, for example, your config management system can dip into, all of a sudden you can have these formerly siloed components listening for events and reacting accordingly. And it's the breakdown of these silos that I think has tremendous potential. Okay, yeah, I mentioned that it's a good way to model systems that need to be both asynchronous and reactive. So, to conclude this definition, a high-speed event bus plus event-driven programming brings us a concept called event-driven infrastructure. So the question is, what can this help us do? Well, many things, but a few of those things are things like gating deploys behind the operational state of the network, right? Right now, we sort of look at graphs and go, oh, okay, is this going to be okay? Yeah, I think this is going to be okay. But we can introduce automation into that step because in theory, we know what constitutes a state that's okay to deploy and one that's not. We can react to service degradation by performing a checklist, right? There was just an Ignite about this concept of a network operations center in which, we have people that sit, and when a bad thing happens, they go through and they look at their checklist and then they do those things. Well, we ought to be able to automate all of that. I believe that most interestingly, we can, in creating a message bus that both our application developers can use and our ops folks can use, we can create the ability to tune the application to the health of the infrastructure, or vice versa. So what are the principles we're talking about here? On a shared event bus, we have events which originate from applications and from systems. We have filters to sort those events and apply rules to them. And as rules are met, registered actions occur. Again, I want to run through the disadvantages because there are both. There's potential for tight coupling between the event schema and consumers of the schema. There's very much the potential for message loss, especially at scale. And it's, again, difficult to reason sometimes about what blocking operations might look like in this model. And hopefully I can go forward here. There we go. Advantages. I think an event-driven approach for infrastructure management is distributed, scalable, and loosely coupled. It effectively functions as a DevOps automation backplane for a system. And it does more than just configuring and provisioning systems at their birth, which I think has traditionally been the focus of the automation space. We talk about how to provision things, how to orchestrate them at their birth. We don't do a very good job at thinking about what the whole life cycle of a system is going to be. And it provides an immediate common programmable layer on top of existing automation and deployment systems. Fine. So, how do we build one? Through much of this this conference, I've heard people say again and again that you should never build your own tools, that you should always take something off the shelf. I think that's completely fine. But at the same time, I don't think that you necessarily need to go and deploy Kafka if your needs are small, A. And B, I think that it's important to understand how one might build a system themselves before they go out and decide to just use something. So we need a couple of things. We need flow. We need an event to be emitted on this bus that would flow to a manager. And we need the manager to check and see if the event matches a registered handler. If it does match, we need a series of rules to check. And for each set of rules which are matched, we need an action to be undertaken. Forgive me as I speed up because I am running a little bit low on time. So the moving pieces here, we have an event bus transport. Right, we have telemetry, right, which is the monitoring that's emitted onto this bus, either from the applications or from the systems which run underneath it. We have actors, right, which take these events and perform actions on them, and reactors, which can react to events as they flow in. So how do we build one of these? We need to handle a couple of concerns. We must handle security. That's a long conversation and one that we don't have time for in the scope of this, but we can discuss it later on. Reliability, we need to be able to serialize data on this bus because, again, we need a common data model. And we need an easy set of interfaces for sending and receiving with libraries shared with languages on the dev side and on the ops side. We need to support multiple architectures, and we need to be able to do message filtering and message routing and what have you. So in terms of topology, typically message buses of this type are pub-sub, right? They're one-to-many. Most implementations are brokered, right? So they're loosely coupled. You can use DDS, what have you. Or you can also do push-pull, which is effectively one-to-one. If you look at typical off-the-shelf message buses, which we'll get to in a second, they support models for both. And so if you want to pull one of these off the shelf and use them, there are a number of them. Most of them are simply language bindings, and that's stuff like 0MQ, what have you, ActiveMQ, or you can get sort of full shelf solutions, and that's stuff like Kafka or Lambda in the cloud, or of course SaltStack, which I happen to like quite a lot. So on the telemetry side, we need the ability for applications to emit events onto the bus, right? Which means that we need little plugins, effectively, that we can hand over to our developers and say, oh, okay, when you want to emit an event onto this bus, simply fire this bit of code, right? It should be light and easy enough that it's simple to port into any language. And it should just be lightweight messaging. This is not the place to push megabytes of data around by any means. So I want to illustrate how simple this is to do in something like Python and 0MQ. To create a message bus and start to push data onto it, that's really all you need. You can do it in 10 to 15 lines of code. So this is not something where you need a ton of programming experience to make happen in your infrastructure. How do you build a reactor? This is me quoting me on Twitter, which is that building reactors or effectively rules engines can be somewhat difficult, but it doesn't necessarily have to be. Because the decision engine, right, something that takes events and chooses when to react upon them, really can be as simple or as complex as they want. But the DevOps idea is to create a simple and shared abstraction for those rules. So, for example, here's something or one way that you might describe a rules engine that both your ops guys and your dev guys can speak to. This is completely arbitrary. This isn't like some published project. But this is YAML that shows something along the lines of, okay, if you see events matching this tag, like client load, here are reactions that should be run. Here are registers. A register in this example would be something that, for example, aggregates data or performs regression analysis or what have you. And here are rules which need to be matched. And if these rules are matched, then you should run these reactions. The point is that it should be very simple to be able to write rules and reactions that are shared by both sides of the house. We need an actor, right? An actor is simply something that's run as a result of an event matching a given rule, right? That could be a call to an external service, a config management call, code that runs locally, what have you. I did create sort of a sample of all of this because I know that some of these concepts can be abstract. If you want to look at it, I put it all there. To review, in order to build scalable systems, we need to be able to adopt the lessons of distributed computing. And we can migrate from simple human-initiated workflows to reactive, programmable systems. And event buses are pretty good, so let's build more of those. Thanks very much.